We have looked until now at terrigenous rocks. We have seen that they derive from the mechanical and/or chemical erosion of pre-existing rocks. We look today at carbonates, a large and very important family of rocks which form in a completely different way. Carbonates form by the extraction of calcium carbonate, CaCO3, from seawater. Very often, extraction is controlled by organic activity. The beautiful corals you see in Barrier Reef, for instance, are great factories of carbonate rocks. This means, for instance, that the production and deposition, which were fully separated for terrigenous rocks, occur now roughly in the same area and are then subject to comparable local chemical, biological and hydrodynamic conditions. Very important to keep in mind. Carbonates, we said, are largely resulting from organic activity. People say that carbonates are born, not made. As a consequence, they have properties very different from those of terrigenous rocks. Carbonates can form very strong structures, sometimes strong enough to cause sinking of ships. Carbonates experience major changes starting from soon after deposition. These changes, which we call early diagenesis, are much stronger than in terrigenous rocks. Think of beach rocks, such as the one you shown in the picture, which have become fully solid within a few years. This is the fundamental equation controlling carbonate deposition. When HO3 is added or CO2 extracted from the system, the reaction will shift to the right and CO3 will be produced. Calcium carbonate can be extracted from seawater by inorganic or by organic processes. We name them abiotic and biotic. Abiotic or anorganic carbonate production is the direct precipitation of calcium carbonate from seawater. Despite the name, we know now that microorganisms such as bacteria play a very important role in assisting precipitation. Possibly the most famous products of abiotic precipitation are ooids, beautiful rounded particles with a very regular internal structures. Rocks composed of ooids are called oolites, and when not fully cemented, form ideal reservoirs with great porosity. Abiotic precipitation is also the process driving the formation of cements during diagenesis of carbonate sediments. One of the important effects of cementation is to eliminate porosity, something oil geologists do not want to happen. By far, the largest amount of carbonates is produced from seawater by organisms. Flourishing communities of plants and animals form the carbonate factory. The characteristics and efficiency of the factory are controlled by living conditions. Because photosynthesis is the process which conditions life of a large number of organisms, light is probably the most important control on skeletal precipitation. In clear waters, light can penetrate through several tens of meters. Muddy waters are not good for carbonates. Temperatures are also of great importance, and most organisms have a strong preference for waters between 20 and 30 degrees. Nutrients are obviously also of great relevance. Different from what you might think, however, the greatest danger is too much rather than too little nutrients. When nutrients are too abundant, carbonate producers are outpaced by other biological competitors and suffer. This is what happens in seas where rivers bring large amounts of fertilizers. Based on the processes controlling carbonate production, we define two types of factory: the tropical factory, the cool water factory, and the mud mound factory. In this course, we will only look at the first one, which is by far the most important. Not surprisingly, living conditions in the tropics are ideal for most carbonate-producing organisms. Producing in the tea factory, the tropical factory, is essentially controlled by light. In these factories, light is abundant and organisms directly or indirectly dependent on photosynthesis thrive. Production rates are very high in the photic zone and basically go down to zero below this. These are the domains of algal mats in the quiet regions and of corals and ooids there where water energies are high. The distribution of the tea factory is then directly related to the intensity of light and to temperatures. Tea factories are typical for the domain between the tropics. Combining the knowledge on carbonate production processes and oceanographic settings, we define two main types of carbonate settings: carbonate ramps and rim platforms. We will look at these systems in the next clips. Carbonate ramps are one of the main types of carbonate systems. Carbonate ramps are very wide domains, generally situated between a flat, low-altitude continental mass and shallow seas. They are characterized by a very gentle slope, typically less than 1 degree. Because of the gentle slope, sedimentary phases in carbonate ramps change very gradually, and facies boundaries are generally parallel to depth lines. For the same reason, the impact of waves is limited and cementation is often controlled by tides. Storms are, however, of great importance. Possibly, the best studied carbonate ramp is in the Persian Gulf, which is also known as the Arabic Gulf. From the map in the slide, you see how large these domains are and how gentle changes are. To reach from Abu Dhabi a water depth of 80 meters, you need to swim for nearly 300 kilometers. Sediments with a sand grain size stretch also for hundreds of kilometers. Along the schematic profile across a carbonate ramp, you can see what kind of sedimentary processes occur at the different depths and the associated sedimentary facies. A first important boundary is that one reached by normal tides. This forms the upper limit of the tidal zone. A second important boundary is the base of waves during normal weather conditions. Between sea level and wave base, waters have a high energy and sediments are mobilized and sorted. The following important surface is the storm base. Sediments above this level are generally untouched, but can be dramatically remobilized during storms. Underneath the storm base, things are quiet. Very different kinds of sediments are observed in the different regions, ranging from evaporites in the supratidal region to the mud deposited below storm base. Let us now look at these various domains in some more detail. The tidal intertidal domain is the part of the system which changes regularly from submerged to dry conditions. In arid regions, such as the Gulf, it is an area of strong evaporation. It is the place of dolomite precipitation and evaporite development. In comparable, less arid regions, lagoons are the normal environment. Moving now towards the sea, we enter the region where waves break. Water movements are here strong and fine-grained sediments are removed. What remains are well-sorted, sand-sized carbonate sands and bioconstructions. The mid-ramp is the region below the depths reached by the waves in normal conditions and above the storm wave base. It is a region of mixed deposits with fine-grained sediments intermingled with sediments with larger grain size. Cross beds and thickness changes document important water movement. In the outer ramp, water depths are too high for sediments to be affected by tides, waves, and even by most storms. It is the domain of marls and other fine-grained sediments, typically well organized with prominent bedding. Carbonate ramps are well known from present-day examples, but are widely represented also in the geologic record. Carbonate ramps form units of key importance in hydrocarbon geology. The second type of carbonate system we look at are carbonate platforms, which are bounded on one or two sides by well-defined rims. We call these rimmed platforms. Rim platforms can be attached to the continent on one side, the left-hand side in the slide, and bounded by steep rim on the other side. From here, the platform passes rapidly to the deep sea. A particularly interesting case of rim platform is that of atolls or isolated platforms, which are fully detached from the continents and limited on both sides by strong and steep rims. Before we start looking in detail at sedimentation patterns in rim platforms, I want to present you the main guidelines followed by these systems. The terminology I use here is taken from Wolfgang Schlager, one of the great carbonate geologists, a person I had the luck to cooperate with. The principles are as follows. The rich get richer. When a carbonate buildup manages to grow higher than the surroundings, it will receive more nutrients and will more light and will therefore have better living conditions and will therefore grow more. During growth, the initial carbonate buildup will become larger and two rims are typically generated, defining an intervening protected domain. These are the rims of the bucket protecting the platform interior. Different from siliciclastic systems, carbonates are able to build very steep slopes, implying that the rim platform can laterally pass quickly to very deep waters. Because it is dependent on life, carbonate production is limited to the photic zone and cannot take place above sea level. In the slide, you see a satellite image of one of the most famous rim platform carbonates of the world, the Bahamas. In the platform domains, the light colors in the image, water depths are very shallow, up to a few meters, and very constant over large regions. The platform is surrounded by domains where the ocean can be up to 2, 3, or 4 kilometers deep. These are the dark blue regions in the slide. The proximity of shallow and deep domains is very different from what we have seen in carbonate ramps. Relevant for carbonate system is the direction of dominant winds and associated storms. These condition currents and impose an asymmetry to the Bahamas platform. Here you see a representative vertical section across the Bahama carbonate platform. You can see the flat platform interior flanked by the rims and the steep slopes. You can also see that the winds are predominantly from the east. This implies a clear asymmetry in the type and architecture of the sediments present in the platform. We will see more in the coming slides. We begin the description of the system from the eastern margin, the margin which faces the strongest currents and waves. Indeed, very strong buildups are needed to survive in this very energetic region. This is the domain of corals and other organisms which can build very resistant frames. The result is a very steep margin which can even be subvertical. As you can imagine, waves and storm impacting the reef will create rubble which will roll down and be transported down the slope. On the other side, the marginal reef absorbs most of the energy and protects the platform interior. Protected by the marginal reef, the platform interior is a domain of quiet, very homogeneous marine and sedimentary conditions. In the eastern side of the Bahama, you see Andros Island, an area which is most of the time above seawater. In the western part of the Bahamas, a very large area characterized by very constant and shallow water depths, most of the time protected from storms and wave action. It is the domain of algae such as Thalassia and Alimeda, which produce carbonate sediments from the skeleton, bind carbonate particles and create large mats. All these very tiny carbonate particles form the carbonate mud, which we call micrite, once transformed in rock. Organisms such as shrimps and worms often burrow through the sediments searching for food. This is what a micrite looks like in thin section. Pretty monotonous indeed. But micrite are not the only sediments found in the platform interior, and the fine-grained sedimentation is sometimes interrupted by coarser-grained sediments brought by storms from the platform margin. The western margin of the Bahama platform is essentially composed of sands. Sands have an angle of repose of 20–30 degrees and are thereby strong enough to protect the shelf platform interior. It is clearly a rim much less strong than the eastern one, but as we have seen, the western margin does not have to support the big storms which hit the region from the east. The steep flanks of the rim platforms are obviously prone to formation of detritus, which is eventually delivered to the adjacent deep basins. Driven by gravitational instabilities and often caused by major storms, large chunks of the rim can break off and glide down the slope. The dimension of the class of these masses are typically variable from that of houses to small grain. While rolling down the slope, mass waves cause often incision and associated channels. Eventually, when reaching deep sea and having left behind a coarse-grained component, these will form turbidites, called calciturbidites. This is the domain of deep water sedimentation we have already looked at in previous slides. We have then reached the end of our long journey, describing the formation and modification of sediments from the mountains to the deep sea. You are now ready to address the more applied issues, hydrocarbon and water, which form the object of modules 5 and 6.